Okay, so we're going to continue 12.4, and we ended with an exercise saying if we have the following 3 points, and I guess let me write these with regular parentheses. If we have the following points, and we're looking at the parallelogram, that is generated by PR as well as PQ. Well, what are these? This is R minus P, which is essentially the vector R itself. And similarly, PQ is just a vector Q itself. And again, here I intended this to be originally just a point, but now it's a vector. Well, let's just write V as 1, 1, 0 and W as 0, 1, 2. Well, the area of the parallelogram, I suppose I could try to draw this. Let me see if, so 1, 1, 0 is sitting on the XY plane. 0, 1, 2 is sitting somewhere here. So overall, you would get some parallelogram like this. It's kind of like that. So this is our parallelogram. Well, what is the area? It's V cross. The area of, it's just the length of the cross product. That's what we proved last time. So what is that? Well, we place 1, 1, 0 here, 0, 1, 2 here. And I'll do this a little quickly. In the ith component, we get 2. In the jth component, we get minus 2. And in the kth component, we get 1. So we have 2, negative 2, 1. And the length of that, so this is just V cross W. The length of that is the square root of 4 plus 4 plus 1, which is 3. So that's the area of the parallelogram. Now a couple of things I wanted to note. So some basic cross products of our so-called standard basis vectors, I, J, and K. Note that, so for example, I'll show a shortcut right now, and I'll maybe just compute a couple of parts of it. I, J, here's K. So if you take the cross product of I and J, so I cross J, it equals the next thing here. So you go to the next one, it goes to K. If you take J cross I, or J cross K, then that equals the next one, which is I. Similarly, K cross I is equal to J. Let me just show one of these. So for example, let's just do this one. So if we take J, which is 1, 0, 1, 0, and 0, 0, 1, well, in the ith component, we're going to get 1. In the jth component, we're going to get 0. The kth component, we're also going to get 0. So this is just I itself, just as an example. Note here that if you go the other way, it actually reverses the process. So suppose you go this way, meaning you do I cross k, you're going to end up with the negative of what you originally had, negative j. If you do k cross j, you're going to end up with minus I. And if you do j cross I, that's minus k. So let's just prove the corresponding one of what we did just now. So let's compute k cross j. So here's k, 0, 0, 1. Here's j, 0, 1, 0. And notice here in the ith component, we get this, oops. We get 0, 1, 1, 0. And then plus 0j. You can see in the jth component you'll get 0. Kth component you get 0, and this is minus I. Okay, so this is kind of a quick way to see the cross products of I, j, and k. And there's a property, so we're going to list several properties, but right now let me list one, or two actually, properties of the cross product. So there are two properties here that we've seen by example, we haven't proved in general, but they are true. It turns out that for two vectors a and b, that if you switch the order, you get the negative of the original. And you can see that in example here, where originally for which one did we do here? We did this one. We did j cross k was equal to I, but k cross j was negative I. Okay, and that turns out to be a general property for any vectors. So let me put this as 1. Another helpful one is, suppose you have a plus b cross c. There's kind of a distributive property. This becomes a cross c plus b cross c. Okay. So this is a distributive property, and it goes both ways. Similarly, you have a cross b plus c is equal to a cross b plus a cross c. And all of these can be proved by just going down to coordinates and proving it. You can just write down the expressions explicitly and see that they're both the same. So for example, I'll do more properties in just a second, but if we had, say, I plus j cross k, right? So this is actually, if you had to write it in coordinates, this would be the vector 1, 1, 0 cross 0, 0, 1. You could do this using these two properties. You could say, okay, well, this is I cross k plus j cross k. And then you could go to, I'll write down our little simple way of remembering at least the cross products of I, j, and k. Well, here we have I cross j, so we're going I cross k. I cross k will be, so I cross k is equal to negative j. So this is actually negative j plus, and then j cross k, do a different color here, j cross k would actually equal I. So j cross k is equal to I, because that's the usual direction, plus I. And so this is equal to 0, negative 1, 0, plus 1, 0, 0. So this is actually the vector 1, negative 1, 0. And you can see that these are actually orthogonal. This is orthogonal. This is orthogonal to the vectors 1, 1, 0 and 0, 0, 1. Just by taking the dot product, you can see that. Okay, so these are Two properties. Let me list a couple of more properties of the cross product. So more properties. I'll just list two more. There's one or two more that are listed in the book, but I'm going to skip them. So let's call this property 3. If you have a constant, let's call k as some constant value. So k times a vector A cross B. This is the same as A cross KB, and it's just k times the whole overall cross product of A and B. So if an individual vector is multiplied by a constant, then it multiplies the whole cross product by that constant. And I'll list one last here, which we're going to use now immediately. A dot B cross C, this is equal to A cross B dot C. Okay. So for 4 here, there's actually going to be a geometric interpretation of this particular dot product. So let's look at the geometric interpretation. So first off, note that if we draw the 3 vectors, let's assume, so let's suppose A, B, and C are given. And we're going to draw them as follows. So say A, let's say B is here, and C is here. And let's take another color and draw A above. Let's say A is somewhere here above. You could draw what's called a parallelepiped. It's like, think of it like a tilted block. So here's another copy of B. Here's another copy of C. And here's another copy of A. And let me use green to sort of dot the dotted portion. B. So this is kind of it's called a parallelepiped. It's basically a tilted block, but we call it a parallelepiped. Think of it like a tilted block. And one could ask, what is the volume of this block? Well, the volume is simply, well, it's the area of the base, and the base is given by the vectors B and C here. So the base, I'll write B here. Here's their base. The base B, so it's the area of the base times the height, and the height can be thought of as, let me use a blue here to draw our height. So here is H. Well, let me redraw that actually on the other side so we can think of it in a different way. Let me draw it here. It's also simply here, right? So this is H. Now, we already know now that from our previous result that the area of the base, this is the length of the cross product B cross C, right? So this is not a dot product, it's just multiplication, by the way, guys. H is just a scalar quantity. This is the volume. Well, what is H? So we know that right here, so this angle is theta. Let's call this angle theta. Now, so cosine of theta is H over the length of A. And so H is the length of A cosine of theta. Now what is this theta? Notice that, and let me say use green for this, the cross product B, so claim is, and you can see this visually, the cross product of B and C is a multiple of, or lies in the direction of H, I guess let's put it that way. Let's write it that way. Lies in the direction of H, right? It's orthogonal to both. If you take this cross product, you want something that's orthogonal to this plane, and let me draw it sort of partially. It's along this line somewhere. So maybe maybe along our vector somewhere here. Let me extend this out. So maybe that green vector right there, that might be B cross C. And actually using the right-hand rule in this particular drawing, seeing that we're rotating from B to C in this direction, B cross C must lie actually above. And hence, the angle theta, so theta is the angle between B cross C and A. And we know that the length of B cross, if you're given two vectors, this is a vector, this is a vector, right? This is a vector, this is a vector. If you take their dot product, that equals the length of A and then the length of B cross C cosine of theta. But this product here is exactly, the area of the base times H, which is the volume. Okay. Well, the only slight thing we have to check is cosine sometimes is negative, and we want the volume to be positive, so we want an absolute value. So it turns out that the absolute value of A dot B cross C is exactly the volume of this parallelepiped. Okay, so instead of doing just a problem which is straight up computing the volume, this is a problem from the book, so it's kind of a nice application. So this is a little example based on this property. So let me circle this as kind of the black box if you want to think of it as a final result. So show that the vectors A equals 1, 4, negative 7, B is equal to 2, negative 1, 4, and C is equal to 0, negative 9, and 18. These are what are called coplanar, i.e. they lie on the same plane, Okay. Now what does that mean geometrically? Geometrically, it would imply that if you took the volume of the corresponding parallelepiped, its volume would be 0. Its volume would equal 0 because it would have no height. It would only have width. So it would only have, i.e. it would be like the volume would be, well, you would have an area of a base, but then the height, this part would be 0 because the third vector would not go outside of the plane. So this is sort of the part that's the plane, which is the base, right? Think of it like here's B, here's C. Well, if A was also on the same plane, then there would be no height, and then the volume would be 0. So essentially what we need to do is show that A dot B cross C is equal to 0. So we just do that. So let's go ahead and do that. So B is 2, negative 1, 4. And C is 0, negative 9, 18. So this is B cross C. And then we'll dot it with A. So what do we get here? We get negative 18 plus 36 I. And then, oops, minus J times 36, right? And then plus K times negative 18. So this is equal to the vector 18 minus 36, negative 18. And A was the vector 1, 4, negative 7. So A was 1, 4, negative 7. So we take the dot product, A dot B cross C. What do we get? 1 times 18 is 18. And then minus 4 times 36 minus 7 times minus 18. And let me do this by factorization. We get 18 times 1 minus 4 times 2. And then, so 18 and then plus 7 here. So we get 18 times 8 minus 8 is 0. This is 0, and hence, hence the vectors are coplanar, because the volume of the corresponding parallelepiped would be 0. Okay. I'm just going to, this is pretty much the end of 12.4. I just want to make one remark here, and this is not going to be on the exam. One can use the cross product to define what's called a torque. And this is kind of basically a rotational force. Again, if you do physics, you'll probably definitely see this. I'm going to leave it to you to read. I'm not going to test you guys on this, but it's a, so if you'd like to, you can read the end of 12.4, which deals with torque. Okay, that's it for now. We will start 12.5 in the next video.